Hello students, welcome back to another video. Today's lesson will actually be the final lesson for this class, and this is going to be on quantum physics. So what is quantum physics? This is the type of physics that is specific to things that are very, very small. So the smallest particles and subatomic particles are subject to quantum physics, which is quite a bit different than classical mechanics, which is what we've been learning about all year. Alright, so quantum physics applies to the smallest particles, or subatomic particles. However, since these are all around us and everything is made up of particles and atoms, this changes the way that we think about reality. The first thing I want to talk about in regards to quantum physics is the quantization of energy. So the quantization of energy was discovered by a scientist, Max Planck. I think it's actually pronounced Planck, but you'll hear Planck all the time in the US. He discovered through some experiments that energy is not continuous, but it's actually discrete. Kind of like how matter is discrete in the sense that the smallest forms of matter are in atoms and subatomic particles, and you can't find masses smaller than those things. Energy is kind of similar. The smallest energy transfers that are observable do not happen continuously. These transfers instead occur in small chunks, where my energy levels will jump from level to level instead of traveling from everything in between those levels. This amount of energy, the smallest amount of energy that is transferable, is called Planck's constant. We use a lowercase h to notate Planck's constant, which equals 6.626 times 10 to the negative 34th power joules. So this tiny, tiny number is the smallest amount of energy possible. You can think of Planck's constant as the scale to which energy transfers by. Another thing I want to talk about in regards to quantum physics is the dual nature of light. So the dual nature of light is that light travels as a wave, which we have learned about previously, and as a particle, and this particle is called a photon. So this is very interesting, because obviously waves are different than particles, right? So does light travel like this, or does it travel as a series of particles like this? Well, the answer is it's both. Light travels in packets of photons that move in waves. This phenomenon was discovered in the two-slits experiment. I'm going to post a link in the description to a video that details the two-slit experiment. I'm not going to go into too much detail, but pretty much the two-slit experiment had light coming in to hit a barrier that had two slits in it. Behind the barrier there was a screen. This experiment showed that an interference pattern as a result of the diffraction that occurs at the opening of the barrier. The waves open out from these barriers, and then these waves interfere with each other in a way to make an interference pattern on the screen. And this pattern that shows up on the screen is indicative of light being a wave. Even whenever scientists are able to shoot light one photon at a time and not as a continuous stream of light, an interference pattern is still made in that case. However, the weirdest thing about this experiment, and one of the weirdest things about quantum physics in general, is that the observation of this experiment can change the outcome. If you repeat this experiment, shooting photons through the double slits, instead of an interference pattern appearing on the screen, there would only be two slits of light measured hitting the screen, right behind the two slits of the barrier. And this of course implies that the light isn't traveling as a wave and interfering with itself, but that it's just going straight through the barrier and hitting the screen. So as it turns out in quantum physics, the observation of a waveform collapses the wave function so that it can only be in one state instead of a probability of states. When waveforms are not observed, the wave can occupy a variety of states, each of these states with a different probability than the other, but still possible. We say that the wave function collapses when it's being observed because only one state is probable at the moment of observation. So this is a very, very confusing concept, and I'm sorry if I did a bad job of explaining it. So please check out both the links below, especially the one on the two-slit experiment. Now let's talk about the applications of quantum physics and what it's done for us so far. So here's a list of some things that the study of quantum physics is responsible for the development of. The first one being atomic clocks. These are the most accurate clocks that we have available to us, and they operate off of the fluctuation of a cesium atom. The next thing on my list is GPS, which we all use to get around nowadays, so it's very important obviously. MRIs are incredibly valuable in the medical field to diagnose and image tissue within the body. Lasers are incredibly important tools for many reasons, and they're used in a lot of experiments because they can shine a single beam of a single frequency of light, and they can also shoot pulses. Cell phones, obviously, one of the most amazing inventions we have, and almost everyone has one. Computers as well, and there's even something called a quantum computer, which has a much higher ability to process information. Okay, that's going to be all for today's video. Once again, I Highly recommend that you check out the links in the description, because quantum physics is really weird and confusing sometimes, but that's why it's beautiful and it's fun to learn about. Thank you all for watching my mini lessons. Have a good one.